So if you'd seen my previous video on binary search trees, you realise that there's a problem with them. What we want is the ability to be able to traverse the tree, search, insert in O of log n time. Now, if you've got a fully complete binary search tree, you can do that or you can get close to that. However, that is a legitimate binary search tree. So the best we can say is that searching and the other operations can be completed in O of h time, which is h being the height of the search tree. Now, unfortunately, in the circumstances that we've just seen there, in that particular tree, O of h and O of n, where n is the number of items, could actually be the same thing. So in which case, there was no point in having a binary search tree, and you could have just had a linked list or a similar data structure. So this is where red-black trees come in to improve the structure so that a fully balanced tree is guaranteed. There's some rules. Number one, every node is given a color. It can be either red or black. The root node is always black. When there's a leaf node, the null pointers coming from the leaf node counts as a black. If a node is red, then both of its children must be black. And the last rule for each node, all of the simple paths from the node to the descendant leaves contain the same number of black nodes. So this is the node class that we had before with the addition of a color property. So we're still going to maintain a pointer to the parents, left and right childs. We're still going to have the key, which is the data. We're just going to keep a Boolean 0 or 1 to represent that color. 0 black, 1 red. Now here's a relatively extensive red-black tree. I want to introduce the concept of black height. So every node has a height, which is the distance from the node to the furthest descendants. The black height is the number of black nodes between itself and its descendants, its furthest descendants. What should be noted is that we do not count the node itself, and all of the null pointers count as black. So for 26, which is the root node, it has a black height of 3 because every possible path to a descendant has 3 black nodes in it. Again, not counting itself, and we do count the null pointers. So let's have a look at building a tree. Simple example first of all. The numbers we're inserting are there in the line, and we're going to insert number 44 first. The rule is that whenever we insert a node, we're always going to set it to be red initially, and then there may be some violations that we have to fix, and we go ahead and fix them. So that's the case here. We put 44 in, we set it to be red, and straight away we're violating rule number 2, which says that the root node has to be black. So that's an easy one to fix. The solution is make the root node black. So moving on, next number we're adding is number 32. Again, we're entering it as red. We're not violating anything there. You see that the nodes all have a black height of 1, so we can move on. 57 gets added next. Again, no violations. Now we're going to add number 18 now. Now that causes a violation because 32 no longer has 2 black children. One of its children, the new node 18, is red. So rule 4 is broken. Now, the uncle of the new node is red. Okay, so number 57 is the uncle of 18. And because it's red, the way to fix this violation is to make both the parent and the uncle black. Okay, now we're okay. Notice that the black height of the root node 44, that's become 2. Everything else is 1, and we're good to carry on. So 33 gets added. It's added as red. There's no violations there. 48 gets added as red. No violations. 59 gets added as red. No violations. So we end up with our fully complete red-black tree. Now that's a simple example, and there are some more complex cases. But before we can understand those, first we need to understand what a rotation is. So let's have a look at some examples of rotations. This is going to be a right rotation. So we're going to rotate around what's number 45 there. 30 is going to take the place of 45. Everything's going to be shunted down to the right. And then the other node, 33, which is circled, is going to become the left child of 45. That's that rotation completed. So here's the left rotation. It's exactly the same, just symmetrical. 45 is going to be rotated around. 56 will take its place. Everything else will be shunted to the left. And then the node there, 47, this time will become the right child of 45. So there are 4 potential violations which could happen when adding a new node. A couple of them you've seen already. So the new node is the root, and it's red, violates rule 2. So all we have to do there is change the root to be black. If the new node's parent is red and it has a red uncle, we change both the parent and the uncle to be black. Now, if the new node's parent is red, it has a black uncle, and the node, parent, and grandparent form a line, what we do is we rotate on the grandparents and recolor. If the new node's parent is red, it has a black uncle, and the node, parent, and grandparent form a triangle, we rotate on the parents in the opposite direction to the node. You're going to see those in the next example. So more complicated now. Starting off with number 44 again, we're adding it as red. Straight away, we're violating rule number 2. So as before, we're just going to set that 44 to be black and fix that one. Number 12 goes in next. Nice and easy, there's no violation there. Right, number 8 goes in. So now we've got the scenario where number 12 doesn't have 2 black children. Number 8's parent is red, its uncle is black. So if you look, the right child of 44 is the black null pointer. So what we're going to do then is think about doing a rotation. 8, 12, and 44 are all in a line. They're all left childs of each other, if you like. So that means we are going to rotate on the grandparents. I'm going to rotate right in this instance. So we end up with that. We're now violating 2 rules here. The root node is not black, and the black heights don't add up on either side. So we've got to complete the recoloring. Essentially means we're going to swap the colors there. So that's that fix. We'll move on to the next one. So number 5, we've now got rule 4 broken because we've got the red parent of number 5. However, we're on this situation here where the uncle, which is 44, is red. So we can recolor those and make them black, and that maintains the rules. 57 goes in next. It's okay, no violations there. Now 49 is next, and that's going to become the left child of 57. We're breaking rule 4 again. The uncle of the new node is black. So if you see, the uncle is the null pointer, which is coming from the right of 57. Now we've got a triangle formation here because 49 is the left child of 57 and 57 is the right child of 44. So we're going to perform a rotate right on the parent this time on 57. That gives us that. We've still got a rule broken. But this time we've got the 3 nodes in a line. So we're going to rotate left on the grandparent here, which is 44. That brings us to that. We can then recolor. And we've got a valid tree again. Last one is number 72. Easy one to finish. There's no violations there. So activity for you, the 3 sets of data there. Draw the red-black trees that will be produced from inserting these data sets. Pause the video, have a go with that, and the answers are coming up in a sec. So for the first one, you should have ended up with that. Second one is that. And the last one is that. See you next time for some more data structures.